Great. Everybody settling in. Great. We're going to start our critical design review of 2025. Big year for us. Excited for competition. For everybody watching at home, we have this microphone. We have a few teams presenting. It'll be mechanical teams in the morning and then non-mechanical teams in the afternoon. I'll leave it off to Peter to... Here's our agenda for the slides, so you can see who's presenting in case you're interested in what comes next and everything like that. You can leave your comments, concerns, questions, anything. We have people watching out and seeing if anybody's interested. For the people here, you're also welcome to ask questions when the question time has happened. And then I believe that's it. They'll try speaking loudly, I hope. Anything else? Great. I'll leave it off to Peter, our chief engineer, to continue.
All right. Thank you, Rachel. That was our vice president. Our president is sadly sick today and couldn't be here, but we're wishing her the best and a speedy recovery. So we're going to start off with a high-level robot overview. This year's system has final storage dimensions of 111.2 centimeters long, 78.2 centimeters wide, and 73.8 centimeters tall. This does fit within the required bounding box for NASA. So our size constraints have been met, and the current system mass is 54.33 kilograms, the final estimate. This is slightly higher than we had hoped at the start of the year, but still a very solid result. The robot will have three main configurations. Configuration 1 is the starting configuration, where the drum is lowered such that the excavation drum is lowered such that it is in line with the ground and the wheels. This is for starting out. This will then immediately be raised up to the maximum extension of the linear actuators to create the traveling configuration, which is the configuration that we'll be using to drive around. And then when we mine, the belt will be lowered all the way, and we will be in the mining configuration. And with that, we now get to the competition overview. Of course, the goal of the competition is to excavate lunar regolith simulant and build volumetric berms with that simulant. The cycle plan for our robot is to start off by spinning to establish orientation and localization. We will then navigate the obstacle zone, and we will mine straight paths to fill the deposition in the excavation zone. So essentially a trenching system. We then return to the construction zone, and ideally we create three spaced piles, each containing ideally 30 liters of regolith. Although this is an upper estimate, and we have some other estimates later on. But that ends the high-level robot overview, and so it is now time for systems.
All right, for systems, we're starting with our concept of operations, which is our con ops. This has not changed from the last review gate, so all of this will stay the same. We also have been talking about integration risks, especially as all the different subteams are starting to bring everything together. So these are divided into three categories. There's high risk, medium risk, and low risk. Low risk, for example, could be there's revisions and requirements of rules at this stage of the competition, maybe not as likely, which is why we have it listed as low risk. Medium risk is more like miscommunication. That's always a possibility, especially in a team as big as this one with as many different projects and subtasks going on. In terms of high risk, that can be like shifts in project focus. With all those subtasks in the different project teams, there's always an issue of if one project starts looking at a new perspective. So a solution to that, try to reinforce timelines with your sub-teams and make sure they know when things are due and how things need to be done. Additionally, forgetting and missing deadlines, this also includes CDR being pushed back a week. So it was originally supposed to be last week, which means there's one less week for manufacturing. So make sure to stay on top of schedules. A full integration plan and risk assessment is found in the systems folder if you're interested in the other parts of that. All right, priorities for systems moving forward. We have 4 big upcoming tasks, which is the systems engineering paper, presentation and demonstration, proof of life, and test readiness review. What all the other sub-teams need to expect from systems is that we will be sending out agents with questions. If you are in systems, that means that either we will be sending you out in person to another sub-team or on Discord. If it is on Discord, please make sure that you copy either me and or Grant on that as well, so we have access to the questions. We're also going to be tracking more manufacturing and testing progress, as well as any potential design changes that do come up. That, I'm going to hand it over to Grant for expected performance.
Yeah, so similar to the last review, we are trying to track how effectively we think the robot is going to perform. So first, we want to track changes in the TPMs. As you can see, we have the PDR values and the CDR values listed here. As was mentioned by Peter, our value for the mass is slightly over what we set as an initial threshold at 50 kilograms. But we don't foresee needing to take any action based on that, or what we're estimating is still well below the ultimate 80 kilogram limit. And so based on these CPMs, we can update our estimates for the total cycle time, number of cycles, and speed at the competitions. So these are our estimates for the burn volume we think we can produce, both at the 30-minute Kennedy Space Center runs and 15-minute University of Central Florida runs. And then here's a scoring comparison between CDR and PDR. The main difference is that we're a little more bullish on our autonomy scores here. We think we can get 300 points by doing a full cycle autonomy, versus we were previously only estimating just automating one segment of the path. Other than that, just the slight change in robot mass changes these values a little. We also have this comparison between using the autonomy versus a skilled operator. This is obviously very speculative now before we have more data with testing with the real robot. But the idea is if we are not using the autonomy or it doesn't work, the human driver relative to the autonomy program can save some time by reducing the idle time and being able to more skillfully navigate the obstacles. So if we make some assumptions about how much time the driver can eliminate, we can see that with these assumptions, you're still going to get less points than the autonomy program. So it's still probably a good idea to run that, but we'll keep updating these estimates when we have more information from the actual robot. So with that, we're going to move on to excavation.
Okay, so to start off excavation, I'm just gonna give a brief high-level system overview. So this year we're going with a bucket elevator system. This is a little bit different than last year when we were running a trencher system. The main reason to switch back to the bucket elevator is due to increased reliability, and just it prevents a lot of jamming issues that we had last year with gravel. It's also a lot more resilient to gravel and just overall a more robust system. We'll be using a 200-watt motor with a 50-to-1 reduction. This gives us a 32 Newton-meter rated torque and a 96 Newton-meter peak torque on the belt. This is about 3 times higher than last year, so we hope that this will reduce our chance of stalling or getting our system jammed. We have an estimated volume throughput of 11.5 liters per minute, a total system mass of 17.84 kilograms, and a total bounding box height of 0.737 meters.
All right, so when it comes to the structure rods, we're sticking with the triple rod design from the previous years. We went ahead and are sticking with the 1/2-inch steel rods. And just like last review gate, we are moving them out to be a little bit wider so that they won't bend. And that pretty much wraps up structure rods.
So this year, when we were looking at ways to tension the belt, we decided to go with a pancake tensioning system. In this way, we have 2 screws that both have nuts on them that would be pushing down on the plate that is connecting to the drum, which allows us to tension it in varying amounts the length of the screw, the 2 drums from each other. And then for the chain that we have to tension for our gear motor, we went with a sprocket tensioning system that allows us to move two nuts that are attached, or not rather attached, but on a screw that is going through a block. This allows us to have a stronger force that allows us to push into the chain, and it is flush. The U channel is flush to the plate so that it is unable to rotate.
All right. And for our dust protection system for excavation, nothing changed a lot since the last review gate. We still have our dust cover, which fits over the bucket elevator. And it has two structural rods, and then it's covered in coated nylon, which is waterproof nylon, and it prevents debris from being shot out from the sides and prevents it from projecting outwards. And it's going to be secured to the structural rods with holes that are punched through the fabric and connected with rings. So it's going to be tied and fastened using rivets. The only thing, the big thing that got changed was there was an issue with it not totally covering the top part near the front drum. So dust was potentially going to be spit out right there. So the issue there was creating more of a curve to cover that area.
So one of the big changes we're making this year is we changed the bucket from a trencher bucket to a traditional bucket. In the past, we've always used traditional fasteners to fasten these buckets, but this year we're going to try and weld them. We've done some test buckets and tested a bunch of different materials and material thicknesses, and we've come to the conclusion that we're going to be using 1/16 aluminum 661 for the leading edge. And to get away with this, we tried 3003 and we tried bending that, but we also tried bending 661. There were some doubts at the beginning, but after testing, we determined that it's okay to bend 1/16 661 for our buckets as long as we make the bends perpendicular to the grain. The buckets are supported by a 1-inch, 1/8 inch thick L channel and is fastened to the belt. Another thing is the bent sheet metal is welded at 5 points to the L channel. And these welds actually turned out pretty well from the test buckets, and we're not too worried about them failing. They seem to be pretty strong. So that's it for the buckets.
So for our excavation system, we're using linear actuators to actuate the system. We used this in past years, so it worked then. So we're hoping it's going to work now as well. We have two actuators, each with an 8-inch stroke, and they give 110 pounds of force, which is different from what we predicted in the last review. It was only 100, so we have a number change there. We're having improved mounting for the linear actuators this time. Previously, we would usually seed the actuators into the support plates, which made reaching the pin in it difficult. So instead of that, this time we're going to have the actuators mounted between the L channel and an extension of the side support plate. So this should make it easier to, tighten the screws, loosen screws, and whatnot. This improved mounting will make the just the mounting process and everything go smoother, so we won't have the issue of reaching stuff again.
Okay, so I'm just going to go over the main things that changed between PDR and now. The main thing that changed with the dust cover was the geometry is slightly modified to not spray dust on PNH. Previously, with our geometry, the top edge of our dust cover was actually not pointing down enough so that dust would get projected on the PNH. So we added a curve to the dust cover to account for that. We also changed the buckets. The leading edge is now 1/16 aluminum 661. At PDR, we had that as 1/8 inch aluminum. And then we also added a sprocket chain tensioner. Previously, we were just bolting a shaft into the side plate, but now we're doing a different system for that. And then we also added dust covers and spacers.
Yeah, so for our DFMEAs, there's not really that many changes from our previous review. The big one is that we took another look at the effects of the buckets falling off or like getting damaged in some way. And in the conclusion we came to is that if they do fall off the belt or if they do like break off and something like ends up getting stuck into the machine, then most likely it'll just end up ripping the excavation cover, which would be unfortunate, but not unmanageable. And that risk is largely mitigatable by just like making sure that they're welded properly and making sure that they're properly fastened to the belt. And that's it.
In terms of manufacturing plans, we're not doing anything too complicated. Most of the parts can be either laser cut or water jet. For the structural rod supports as seen in the top right, we plan on milling or CNCing these and then sawing using a saw to cut out the slot. For the U-channel for the tensioner, we plan to cut that in the mill. It shouldn't be too complicated. And then for dust covers and spacers, we plan on 3D printing these. In terms of priorities moving forward, first off, we'll implement feedback from CDR, and then we'll begin preparation for manufacturing and create engineering drawings. And then we also plan on fabricating more test buckets and begin testing the buckets on our mining force rig. So that's it for excavation. So now we'll take some questions. Alex.
These sort of things be the two things like how huge of those are consistently happening, one that's not better than the other.
So last year, we had a very similar system. It didn't seem to be a huge problem with over tightening one side as long as you alternate doing one hand crank on one bolt and then switching to the other. It didn't seem too much of a problem last year, so I'm not too worried about that. Peter?
For making the nylon sheet to cover it, we've thought all about how you're going to make sure the sheet is the correct size, how you're going to make sure the holes are in the correct place. You're going to need to make jigs for putting these holes in the correct place.
So I've thought about it a little bit. So we plan on cutting out the fabric to match the size that we need. The fabric is somewhat flexible, so that gives us a bit of leeway in terms of placing the holes into the fabric. But as to the location of the holes, that's something we need to still determine. And we plan on buying extra material just in case we make some errors. This is a pretty new process, so it will probably require a little bit of experimentation, but overall, due to the flexibility of the material, I'm not that concerned about it. No?
When it comes to this dust protection system, what thickness of the material is made of?
It's made of 1-inch aluminum. Or wait, sorry, 1/8 inch aluminum.
So I would assume that this part is not structural.
No.
1/8 inch aluminum, especially given how large the part is going to be.
Yeah.
You definitely get away with 16-inch aluminum, given this should be under basically no load. And you probably would want to do weight reduction rules on it, because this is it looks like it's basically just a large piece of metal without any like purpose of being a large piece of metal. So I recommend trying to reduce the weight on that part.
Okay, we'll look into that. I think the weight of the total dust cover assembly minus the fabric is about 0.9 to 1 kilograms. So we can definitely cut off like a little bit of weight there for sure.
That's 2 pounds. It can easily be cut down.
Got it. Alex?
Are you worried about that holes shearing or?
I'm a little bit worried about it. We're trying to mitigate this by putting a 3D printed piece in between. Hopefully it's not a problem. We did.
excavation has, but I'll ask, and taking the entire way of the system of the robot, with the front wheel longer.
Mhm.
And, so that's a lot of weight to put on performance.
Yeah. Oh.
In regard to that problem, you all can very easily check to see if that is going to fail through shear or bending. That's the very simple basic steps in it.
Yeah.
But, so you can ensure that it can take the full weight of the robot. Also, a kind of question, it looks like to support the strut rods, you have a custom machine that component. Is there a reason that you shifted over to a custom machine component compared to an off-the-shelf part as opposed to previous years?
Yeah, so we switched to this component because this custom component has a much smaller footprint compared to the off-the-shelf parts. And due to moving the strut rods outwards from last year, using those off-the-shelf parts caused some integration issues. So that's why we switched to the custom parts. Hans?
Are you sure that chain tensioner is actually going to tension the chain fully?
We're pretty sure there's quite a bit of the chain tensioner has quite a bit of throw. And as you can see in the image on the bottom left, that's like, the chain is like, we can shorten the chain. Like that's not like what it will actually completely look like, but I believe that the chain tensioner has enough throw and cause enough displacement in the chain to fully tension it.
It might be worth looking into it. It's something that we do this year. We had an adjustable chain tensioner design to count that.
Okay. Peter?
I've got some questions from the YouTube chat here. First, Sophia asked, are normal rivets being used for the dust?
Yeah, we're using normal rivets on the dust cover, and for the holes in the actual fabric, we plan on using a grommet tool and supporting those holes with metal rings.
Okay, and then a question from Naren Brown. What kind of testing went into the buckets?
So you mean like, does he mean destructive testing or just testing like our processes? So in terms of testing the process of welding, we experimented with various different sheet metal thicknesses and different L channels. So originally at PDR, for the L channel, we had used a rounded L channel, but now we switched to a squared off L channel. This is due to like some issues we had with the gaps for the welding. So that's why we switched to the squared off L channel. In terms of material thicknesses, we just tried bending different various sheet metals. So I think we tried 1/16 3003 and then 1/8 and 1/16 aluminum 661, and we determined that 1/16 aluminum 661 would be the best. And we're able to mitigate like the issues with the bending by bending it perpendicular to the grain. In terms of bucket testing, like the quality of the welds, we haven't done any of that yet, but we're in the process of constructing a rig to test that, where we essentially will just be testing plunging the buckets into the ground to simulate sort of mining. Just from looking at the buckets and just playing around with them, they do seem to be pretty strong at the welds, and we don't think that would be the failure point of the buckets. So it's not too concerning in terms of bucket leading edges falling off. Al?
Yes, we do bucket testing. You technically don't even need to actually do any mining to do the testing.
Yeah.
You could, in theory, just try and pull them and see what force it takes for them to fail in that manner, whether you pull directly outwards from the bucket or trying to pull it down, like trying to pull it down, or pull the leading edge down, which will simulate your learning process. But also, how are you able to source? I assume that you're using 6061
Yeah.
for the L channel.
Mm.
Are you able to source 9-degree? But the master doesn't have the straight edge 661. I mean 663.
I'll have to double check that. I'm pretty sure they do now, because I'm pretty sure I purchased some recently.
Hans?
Is there any way you're ensuring that both linear actuators are synchronized?
I'd say that's more of a like software thing. We haven't had issues with this in the past, so I don't foresee it being a problem this year. I don't know if Alex has anything to say on that.
If we tell them both go up, they both go up. So it's significantly under whatever strength. That's use 150 calculator actuators, and there's a situation where we're using 300 pounds anywhere near this level. So on the one, I did a lot of work with summer in 6061. The reason you're having a benefit against the grain is because it worse alloy of aluminum 10. I would really recommend it if you benefit against the grain or using a failure point.
Yeah. Okay, so I do agree that 661 is not ideal for bending. The main reason why we're going with 661 over something else is due to its weldability. Because 1/16 aluminum can be difficult to weld, and 661 is a bit easier to weld than other aluminum alloys.
Okay.
What kind of replacement parts do you guys gonna have? Like you mentioned that fabric cover can grips, it's probably good to have some more of those, but like, are you gonna have a spare belt that bends, for example?
We do not plan on having a spare belt. The belt is very strong, so I'm not worried about it failing. In terms of replacement parts, we do plan on making extra buckets and also plan on getting a bunch of extra master links for our chain because we've had issues with those in the past. And I think that's pretty much it for spare parts. Alex?
That's slightly different though. So on your chain connector for your sprocket belt, your U channel, mentioned that the U channel was flush with
Yep.
How are we getting a nut on the other side?
So it's actually not fastened to the plate there. It's fastened to the plate in those there's two bolts in the bottom part of the chain tension. That bolt is actually the bolt on the top is actually threaded into the shaft that holds the sprocket, but it doesn't go all the way through to the plate.
And the shaft is inlaid into the U channel. So it's all the bundle interactive. Right? Are you using the same interactive as last year?
Yeah.
Those are 150 pounds.
Okay.
It changes nothing.
Yeah. I know like they had the exact same data sheet too. It's kind of interesting.
Yes.
Okay.
What kind of testing did you do for those beds? How do you know?
Just from a process standpoint, we bent the different types of metal, and from what we determined, like based on the process of the weld, that's the one that produced the most ideal like situation for the welding process, and the bends didn't seem too problematic, and in general, we're not worried at those bends being a failure point for the buckets. Because the welds actually turned out pretty good, and the bends actually didn't look that bad.
And it's 50 series and 60 series should be wrong. And the reason you're bending against the grain, 60, 61, and 1000 pounds. It's treated to bend that huge rectangle.
Okay.
Do some kind of NDT testing.
Okay.
It's pretty well. 5052 is pretty low growth. It's arguably in your well. And you can bet.
Okay, sounds good. We'll definitely probably switch to that then.
Higher than and patents are not really nice.
Okay.
I'll go for that. You channel it. You can take a saw and put a handle on.
That's for the part on the top right. So it's a pretty small gap. So we don't think it could around, I think, 0.1 inches. So we're not completely sure if we can do that in a CNC or a mill. So we figured out that it might be best just to use a saw for that, or a band saw. Just because we're making quite a few of these, and the tolerances on that gap don't really matter that much. So that's why we're using a saw for that.
I don't think the stock can give you the ones you need all. Are usually they're just going to give you. I look at an EDF machine or one.
Okay.
On that note, there are tools called splitting saws, which you can find which mills have, which people have access. We'll probably just use the splitting saw, I think.
Okay. Any more questions?
Looks like we have a YouTube question from Nate. Was using steel tubes over shafts instead of the strut rod. We've seen previous years the main failure mode is buckling, so you might be able to get away with tubes with a quick buckling.
Is this for the struck rod?
This is the strut rods.
So we looked into it a little bit. We did some basic FEA, and it looked like there might be some bending issues with some tubes. Maybe we could look into replacing one or two, maybe just one of the struck rods with a tube. But we'll have to look into that more. But in the past, these struck rods have worked pretty well. I know hauling them out to tubes might save some weight, so we can look into that a little bit more. Kyle?
One thing that isn't super clear to me, what is like the assembly of the chain tensioner on the top of it? And like, is there a bolt that goes through the entire thing that acts as the shaft for the sprocket? Is there an actual shaft in there?
I can describe it. So basically we have a U channel, right? And so we have the U channel, and within the U channel, we have a shaft that's inlaid to the bottom that's on the plate. And then through the top, we're screwing into the shaft. And then around the shaft, we have two spacers for the sprocket, and then we have the sprocket going around the shaft.
The sprocket is a bearing.
Sprocket is a bearing.
Does that mean that the shaft that the sprocket is resting on only has one support point?
That's the two.
It has the screw and it's inlaid into the U channel. So all the forces going inwards.
So the shaft is like stacked into the.
Practically, yes.
Okay. Yeah.
Yeah.
Yeah. It wasn't.
How are you gonna manufacture that? You're gonna cut a little slot to the sprocket fit in.
So we're buying the U channel off of McMaster, and then we'll cut down the material and drill the holes into it ourselves.
So you're saying that inside the inner side of this U channel, you have a little slot tensioner. It's kind of slots in.
It's just it's a hole on one of the sides of the U that's
a through hole.
Yeah, like a through hole. Yeah. All right, so I think that wraps up the questions for excavation. I think we'll move on to deposition.
Good morning.
So this year we are starting with a brand new design of a deposition system. Last year we used an auger-based deposition, and now we are going to use a conveyor belt. We're going to use 0.06-inch thick neoprene rubber belt with 24 by 10 inches of usable surface which the regolith can be collected on. It uses polycarbonate and 3D printed material components of the wall to keep the regolith inside. It's using the new brushless 200-watt motor and takes about 7 seconds to deposit. It weighs 9.910 kilograms. It can collect up to 20 liters of, and it can collect up to 20 liters of the regolith. So for the structure, we are going to use two 1/8 aluminum side plates connected together by 2 connecting bars and L brackets. We did some testing on FEA and determined that 1/8 of an aluminum is going to be sufficient for structural stability. We're using, for deposition motor, the main thing that changed was using different gearbox. Instead of using a 50-to-1 gearbox, we're going to use 100-to-1 gearbox, which will give us a 30 rotations per minute. And we're going to connect it using the 25P chain. To keep the regolith from escaping, we're going to use a combination of polycarbonate sidewalls and a 3D printed triangular ramps. The triangular ramps are designed so they can be easily adjusted during testing in terms of dimensions, and they're supposed to come as close as possible to the surface of the belt to prevent any regolith leakage through the sides or through the front of the system. We're also going to use custom rollers and idler pulley. The main reason for using custom rollers is that we couldn't find ones with the appropriate dimensions. They're going to be made by machining as 3/4 of an inch shaft and using flank bearings to press into the sidewalls and onto the shaft. The main reason for using custom idler pulley was so we can lathe it for a self-centering design to prevent the belt from slipping to left or right. And another reason was the price consideration, because manufacturing custom idler pulley would be like 10 times as cheap.
Just a little bit more on the whole belt centering thing. You can kind of barely see the little curve up, which would provide another force to prevent the belt from moving on this pulley. Got a 2-inch center diameter and then 1.95-inch diameter. Going on from there, for our dust cover, we currently have 3 points in which it's mounted, these 3 bolts. Not pictured here. It's going to be split into 2 components. Due to the position of deposition with the drivetrain, we kind of have to put 2 components up like this. So imagine this split in half, and we put top down and then bottom up, just because drivetrain's in the way. This bottom part will be flush with the side plate. For our tensioning systems, we are kind of doing what we did last year. You can see with our the one for the motor on the right side here, it's just pushing, it's wrapping around the chain is wrapping around that additional sprocket on the right side, and that sprocket can move to the right. There's a slot it can move, which will provide any more tensioning if we need to. And then for the pulley, we have a screw that we can adjust the position of that pulley. For our DFMEA, biggest changes for us in terms of like mitigating our issues with the self-centering idle pulley, we're not worried anymore about like the belt shifting or moving during running. Another thing is the new ramp design. We don't think that dust being stuck is going to be a significant issue anymore. And after like further calculations and analysis, we don't think the belt can break like during tensioning or overloading.
So just to review everything and go back to the post-PDR changes, one of the big things we did was to connect the structural side plates to improve the stability of the system. We also modified the belt tensioner design. We decreased its length to decrease momentum on it. We increased the bolt size and added a flat surface to the idler pulley shaft to prevent. We reduced side plate thickness to a 1/8 inch of aluminum to reduce the weight, and also because it was sufficient integrity. We also added locks to the connecting side plates to connect to the plates connecting the side plates. So this way, our software team can access the data about the amount of regolith collected by the deposition system. We changed the design of 3D printed triangular ramps and modified it for actual manufacturing, adding some interlocks and the holes for the heat inserts to improve mounting. Also, we are going to use PLA material for all of the future 3D printing. We added dust covers. We replaced 50 to 1 gearbox with 100 to 1 gearbox to increase the deposition time and decrease possibility of belt slipping. And we decreased the gap between the balls and the belt, and we implemented the self-centering belt design. For our manufacturing plan and schedule, for manufacturing the aluminum side plates and the connector plates, we're going to use CNC mill. For manufacturing the idle conveyor pulley with a convex self-centering design, we're going to use CNC lathe. For polycarbonate parts, we're going to use hand tools, but we might have an opportunity to use CNC in the future, depending on the availability. Right now, it's not a really high priority because it can be manufactured easily, and we want to prioritize other components which require CNC. For spaces and the 3D printed ramps, we're going to use 3D printing. We will use broach to manually key some of the shafts, and we will use manually to make the pin tensioner for the chain tensioner design. And for connecting the belt together, we're going to use splicing. Right now, our current plan is to use mechanical splicing, but we're also looking into thermal or using glue. So our priorities moving forward are creating drawings for the manufacturing phase, fabrication and sourcing of parts, assembly and testing. Thank you. Any questions? Peter?
So first we have a question from the chat. Val asked if we looked into any active or passive dust mitigation for the triangle damage in the polycarbonate wall. We might be able to get some good ones on the rubric coatings or surfaces.
We have not yet, but one of the main advantages of using the triangular ramp is that we can easily modify its design at any point during manufacturing, and it's very easily to replace after the system was assembled. So if we will have any ideas on how to modify it, we can create a second version and test it. Hans?
Why did you change the 101 gearbox?
Because 3.5 seconds of deposition was way too fast, and we would essentially have to run the motor at like half the power. And 101 gearbox has almost identical size and almost identical weight, and it will also increase torque.
Not needle. What, like 60 Newton meters of continuous torque, 200 Newton meters of peak torque? It's not that hard to motor at speed. You get the one who will be running the motor at speed.
I see. I mean, we can potentially also change back to a 50 to 1 gearbox. Yeah. Oh, Kyle?
It also sounds like why not just go with a less powerful motor? You don't need the speed or torque. Why use such a powerful motor?
So right now, Purdue Lunabotics updated all of its motors to this 200-watt brushless design. So it's the same as Drivetrain uses, and mainly just standardization. We have the same motor for everything.
A little bit more. Did it like motors we have sitting in a test right now? These are 200-watt Brightness motors. Those motors are lighter than our current excavation deposition motors, which are 100-watt motors, and are also lighter than our Drivetrain motors, which are 30-watt motors. Yeah, they're lighter and 2 to 5 times.
It's more, I was wondering, not, why aren't you using the weaker motors last year? Since you were buying new motors in general, buy a less powerful motor that could be substituted in that uses something.
I think for this exact model, 200 watts is the least powerful version. We also have a 400 watt, which would have been insanely more powerful than we need for deposition at least. Another Kyle question.
Your idler, it looks like it's only supported on one side.
Where?
Idler tension, not the bellows, the chain tension, I'm sorry.
There.
How's that mounted to the rope?
In the same way as it was last year. So the tension, it's not shown on a screenshot, but the tension pin essentially, the slot is smaller than a tension pin. So when it extends through the slot, it's going to have thread, which we are going to put a lock nut on. And then it's just going to be wider than a slot on the other side. So it's just going to create clap onto the side plate.
Is it secured on the space?
Yeah.
It is essentially the same design as used last year.
Okay, I think what's different is the fact that there is a step, and I think that there was last year on the slide. I don't remember this.
No, it's a business.
Yeah, it's just different angle. Yeah. Alex?
On the long development at their are you concerned about manufacturing costs just about the tightest tolerance that you can? Yeah, so I need to be
I'm not too much concerned about it because one of the things is they don't really have to be providing any power. They're essentially just a structural just to support the weight of the regolith. So even if it slightly slips, it's not really going to be that big of a deal. Peter?
On that note, the way that we do press fits, the way that we started doing press fits last year and hopefully we'll continue doing them is we cut short answer no, because we cut the whole underside with the laser cutter and then we cover with the boring head and slowly open it up to 1,000.
The custom roll. Unless I'm looking at this wrong, the pressing on the outside of the shaft.
That's incorrect. They're very pressed into the side. Unless
I know they will be pressed on the sidewall. Yeah.
There's no.
Yeah, so
the sidewall is not visible.
When you go back to the main overall.
Yep. So
yeah, so you can see that the bearings are sitting in the sidewall. The two bearings are right. So they're gonna press this side.
And so that center shaft just kind of floating around.
yeah.
Yeah.
Okay, that's fine. Next to the chair.
No, it's just in there, it's there, right?
Yeah, but not like full pressing.
No, it's in there. No.
All question about is on the definition. Can you go to slide 36 first?
Yeah.
Right, so you see the side of the section of the wedges. Mounting those wedges.
So the wedges have holes for heat inserts, and the heat inserts are designed to be supporting for 1024 bolts, and we're just going to put the bolts in and connect them to the triangular side plate. It's not going to be connected to the aluminum sidewall for ease of access, so it just has a larger clearance holes, just so like an access hole, just to access it. So if you go to like the overall TLA, the larger holes are going to be used for access. Hans?
Yeah, with those triangle ramps,
yep.
Those actually like mounted. Like you have like keys that inserts. It's a 3D printed part. Or
they're going to have holes for inserts, for heat inserts, and then the polycarbonate walls are having precisely aligned holes, so we just put in the bolt and yeah, with heat inserts to keep them in place. Kyle?
Why did you choose a neoprene rubber belt rather than like canvas or something else?
So we were just looking at different materials, and neoprene rubber belts, they have relatively, the belt we're using has a low friction top, which can help with regular sticking, and with potentially touching triangular side ramps. It was very thin and relatively strong, so it will not break under any loads which we're going under tensioning for the loads. And it was one of the cheaper options.
Okay. Because have you used neoprene rubber before?
No.
So in the past, I have dealt with neoprene rubber. It is very bendy. So you might not actually be able to get the impact and have this thin gap through the entire length of deposition. I don't think that you're going to get that without tensioning the belt very high. Yeah. Because neoprene is both flexible and very stretchy. So, especially given you have a 60-valve belt, I'm very concerned about that working well, rather than using something more conventional like what we had done for Deposition or Excavation a few years ago, was using a canvas, a thick canvas for the belts, which I think would probably work better in rubber belts in this situation. Especially if you're going to use mechanically make the belt or something.
Yeah, I think, yeah, we might look into the canvas belt as well. Hey, Peter?
Question from the chat, how does the tensioner get attached to the robot? The tensioner is pressed into the D shaft, not the triangle wall. So yeah, that one bottom left.
Bottom left. So it has two threaded bolts on the other side, and it's going to have two bolts from the inside, from the other side of the side plate going in. Alex?
For your side plate, you mentioned if you were going to be CNC cutting them.
We can also water-jet laser cut them.
Water-jet laser cutting instead of CNC.
As long as it's manufactured by using some kind of computer operating tool, it should be fine. Julian?
I know we're not dealing with very large amounts of weights on the belt, but if you look into the belt potentially buckling, since you're sort of pushing on, when you drive the belt, you're sort of pushing on it versus pulling on it. Well, traditionally, belts, the motor, I think you tend to put the motor, if you have a two-way belt, put the motor on the chin, because when you drive, you tend to want to pull off because, from what I'm pulling, it's not explained, but I'll talk to you a little bit later about it, but that could be potentially a potential failure mode of the belt. But we're not putting that much material on the belt.
First, can you elaborate on what you meant when you said you're going to use hand tools to make the polycarbonate sidewalls?
Probably using saw and hand drills to manufacture the holes and cut it to size.
I would suggest that there are methods by which we could CNC this very easily. The water jet could do it, I believe. The water jet could do it, the plate mill that can do it. I don't think there's a need to introduce hand tools into this business.
Yeah, I would much prefer to use CNC. It's just not a priority because this part can be manufactured using hand tools. But I would prefer to use CNC.
Drivetrain is also using polycarbonate. We're actually use the battery of BADC. Joints.
Okay.
Also using Drivetrain software's camera covers.
Okay.
So we can just make that all. Yeah, that's what we did that. No.
Okay, perfect. I would much prefer to you do that.
Yeah.
And do you have another question?
I do. Looking at that chain tensioner, it looks like a very small, or not chain tensioner, the chain itself looks like a very small clearance between the chain and the dust cover. Have you looked into that, where the chain could potentially rub against the dust cover?
We didn't think that like there was a chance for the chain, because the tensioner is there, that the chain would like in any way move into the wall. We can always make the dust cover itself larger if that's the case. Just replace a 3D print if need be, but
Even under a very well tensioned design, when you're actually running under it's
Okay. Kyle?
Are you worried about abrasion of the belt? Because regolith will get underneath your triangular parts, no matter what, now be a moving surface with a stationary surface. Are you worried about the belt getting more away and potentially losing more regolith as time goes on?
Yes, we are worried about that, and we also mentioned that in the DFMEA. It still haven't changed from the last year because we still from the last review, which also was last year, because we're using the same belt material, but so our current plan is to just visually inspect it after runs and potentially look into different materials which might be more abrasion resistant. But the main issue right now, at least with the rubber belts, is the most abrasion resistant belts. They will not be compatible with our size of pulley because a lot of them require like a 10-inch pulley, while we have 2 inches. Peter?
Question from the chat, what material is the dust cover made out of?
3D printed PLA.
And then another question, you said on manufacturing plant you're going to use a broach to key shafts. Did you misspeak? Are we trying to key shafts or are we trying to key sprockets?
We might have to key one of the shafts unless we can source it. There were some issues with like finding the exactly right key and the right length.
Okay, because the broach is used to make an internal keyway on an internal board. To key a shaft, I would assume just an end mill.
Yeah. Okay.
Yeah. Which is much easier and better.
Alex?
What is the green rubber?
It's going to be from a Mastercard, probably.
It looks like it's going to rather carpet. Remove the right side.
Yeah, it just needs to be a 10-inch wide sheet of rubber. Hans?
It seems your aluminum sidewalls are 8-inch thick.
Yeah.
Most of that. So, done any FAA analysis on that, whether that 50-60-inch or at least have some weight saving goals, since ideally there should be minimal load on the sides.
I have not done FAA on the 16th-inch wall because our main priority was going from 40-inch to 1/8-inch. We can do this, but also I'm gonna doubt that. I'm not sure if this will work because basically one of the sidewalls is the only point of support for the motor and the gearbox assembly. So I'm afraid at least that wall might break. If it's going to be 16th-inch, it might bend under the weight of the motor.
The other side though, maybe the weight saving goals there.
Yeah, we will definitely consider weight saving holes.
Yeah.
Are there any other questions?
So like for how much sag can you tolerate? Because I know the density of the regolith, but I just looked up like what 20 meters of like sand weight. And it's like 60. Like how much sag can you tolerate in the middle when it starts to get problem?
I would say about maybe 1 inch, half inch. But also another thing is Mainly the regolith will mainly sag in the more like to the center of the belt and not as much to the sides. And yeah, I haven't really looked that much into it. But also one of the things with the 3D printed side ramps is that they're designed to be replaced at any moment after the robot's assembly. Oh yeah, Peter.
Maybe I misunderstood the question. That felt like more of a structurally, are we concerned that that much weight on the belt might cause problems?
It shouldn't. I was running a PA with like the maximum with a 40 pounds of 40, I think 40 kilograms or 40 pounds of regolith, which was calculated using the relative maximum density for the regolith provided by NASA, and the only concerns would be the belt sagging, but also it will not cause any issues with the structure with side plates in terms of tension. Alex?
If you discover the belt does sag, let's take what are your plans to go in media
Adding more rollers and increasing tension, and potentially changing the design of the ramp to the side ramp to prevent loss of regolith through the sag.
Based off of your current material selection, your belt will sag a lot. It probably will contact the bottom then.
Yeah.
neoprene rubber is very. Imagine making the belt out of rubber.
Okay. I will look into replacing the material for the rubber belt. Are there any other questions? Okay, thank you. Next up is Drivetrain.
Okay, we're going to start Drivetrain with a high-level system overview. Those dimensions up there, 34 by 28.6 by 13.5. That is length, width, height of our system in inches. That is within the bounding boxes. Our system mass is currently projected to be 19.3 kilograms, which is just under the 20 kilograms we allotted to us at the beginning of the year. We are going with a linear gearbox arrangement, keeping the chain drive with an improved chain tensioner. We have a new box grouser wheel design this year, as you can see in the image. And we decided to go with 1/8-inch square box tube. We considered weight savings holes, but after doing some FEA analysis, we found that weight savings holes were just not worth it. Okay, clearance and mass estimates. We currently project a ground clearance of 4.43 to 5.19 inches. The difference in that range is whether you consider the ground clearance, is really up to sinkage. 4.43 would be worst case scenario where we are fully sunken into the bottom of the wheel grousers. And 5.19 would be what you would experience if you were driving on a concrete floor. That's from the very bottom of the wheel as shown in the image there. And there's our system mass again. And now we'll go into gearboxes.
So for the front gearboxes, we'll be using number 35 chain with the 12-millimeter wheel shaft. We'll be using rivet nut mounting to attach it to the frame, and we'll have a shaft collar for the wheel. For the rear gearboxes, they'll be connected with that chain and they'll be driving them. It'll have a 1-to-1 internal gear ratio, and the gearbox assembly for the motor will be 50-to-1. That is roughly 36% of motor power will give about 1 feet per second with 32 Newton meter rated torque and 92 Newton meter peak torque. Same chain size because they'll be attached to the front ones, and we'll also be using rivet nut mounting for these as well.
So this is our improved change tensioner. The main difference we had in between our CDR and PDR reviews is that we made our sprocket larger just to accommodate the tension we want to get within the thing. So the tensioner is a 4.5-inch diameter sprocket with a 1/2-inch ball bearing pressed into it, and that sits on a 1/4-20 bolt, which is fastened to both sides of the frame with spacers to keep it in line. And then this is our chain guard. It is bent polycarb. This is just going to be mounted to both the gearbox and the frame to keep the chain safe from all the dust.
All right, for frame, the final mass for it is 4.07 kilograms. The overall dimensions are going to be 32 inches by 16 inches. The box tubes are going to be 2-inch by 2-inch squares that are an eighth of an inch thick. The rear joints are going to be made of 4-inch by 2-inch by 1/8-inch gusset plates, and then the front joints will be made of 2-inch by 2-inch by 1/8-inch thick L brackets. As Hans mentioned earlier, we explored weight saving holes, but after doing simulations, the mass that we would be able to lose from doing them was so minimal that it's not worth it.
Okay, onto wheels. So the big change from CDR to PDR is that instead of the floor pieces being one continuous piece of sheet metal, it's now composed of 24 individual floor tabs. And just to give you a refresher, this wheel is composed of like 2 main side plates that we call the rims, and then individual grouser pieces, and then individual floor pieces. And then these grouser and floor pieces are kind of interlocked with the wheel with these tabs that are cut out from the rim piece, and then the floor and grouser pieces have corresponding tabs that slot into them. And so these 2 rim pieces are squished together with bolts and standoffs. This wheel design has 8 of them at each individual spoke of the wheel. And so, yeah.
So the dimensions of the wheel, shown by the blue line is the width, which is at 4.25 inches, and the effective diameter indicated by red is 12 inches, and the outer diameter indicated by the green is 13.5 inches, and the grouser length is 3/4 of an inch, and the weight of each wheel is about 3.17 pounds each.
So we're planning on cutting all the sheet metal parts from this wheel with the laser cutter and the BIDC. Some kerf testing does need to be done in this laser cutter in order to find out the correct tolerances of the individual tabs, the grouser and floor pieces. We also need to do some deburring, particularly on the 1/8-inch rim pieces. And so we made a prototype of this wheel, and assembly of the individual floor and grouser pieces into the rim, as expected, was kind of difficult. So of course, having 24 of them will be more difficult, but we have some plans on making this assembly easier with a 3D printed jig, for example. And also, when we improve the tolerances of the individual floor and grouser pieces to better suit the rim, we expect it'll be a little bit easier because they won't be, the floor and grouser pieces, when we assembled them, were kind of like floppy like this. They'll be more straight when the tolerances are better. And a bunch of other things will make assembly easier, but
So the DFME hasn't changed much since PDR. The main issues that we potentially might see are the frame bending or breaking, which hasn't been an issue last year and we don't think will be an issue this year. Parts of the drive failing, which again, we haven't historically had an issue with. And then wheel sinkage, which we have increased the diameter of the wheels to account for. Other than that, we don't think there should be any huge issues with the drivetrain system.
So since PDR, we really got 2 main areas of feedback. First being the tensioner. We have increased the tensioner sprocket to ensure that we actually are going to be able to get proper tension. One of the other concerns was us when we tensionate, it bending in the sides of the box tube. We are planning to use 100% infill PLA spacers in there to help mitigate that and hold the inside
of the box tube apart. And then the other big concern was the wheels. We've significantly fleshed out the design and we've made a prototype, and we've increased the manufacturability of it. We've been looking into that a lot and are planning to get that started right away with those curve tests. Other small things are things like dust covers and more access holes. That leads us into our manufacturing plan. As I said, we're going to start with the wheels, and that would just be in the BIDC on the laser cutter or the water jet. We're going to start with that right away. Then at the same time, other members are going to be doing frame plus gearboxes also in the BIDC. And then lastly, we're going to be working on the frame brackets and then other miscellaneous parts. Luckily, most of our system is CNC machined this year, which means we have very few drawings. The drawings, I think, actually are just sprockets, since we need to bore our sprockets to get to the 12mm shaft, and then keys. And that's all our drawings, and then 3D printed parts. And then we should be good for assembly. So this also doubles down as our plan moving forward. Questions? Peter.
So for the chain tensioner, the sprocket, we're going to need to bore out that interior to build the rest of the bearing.
Not for the chain tensioner. We will have to bore out the gearbox sprockets to be able to get the 12mm shaft in there. The shaft.
Go back to that. Then what's the half-inch ball bearing? Is that just the side that's in the sides?
The sprocket we buy has a 1/2-inch diameter hole in it, and then we're just going to press a 1/2-inch diameter ball bearing into that.
Are you concerned about the hole being too big for a broad press fit?
Not really. I haven't really thought about that. Even if it wasn't perfectly machined when it was manufactured, it shouldn't really matter since it is fully defined on the sides by the spacers and box tube anyway.
Okay.
But we will have to bore out the sprockets for the gearboxes, and the sprockets we're planning on buying are meant to be machined out in the bore. Alex.
Somewhere.
That is an excellent observation. Yes, we realize this. We are going to add, it's very similar methodology to last year, eye bolts in the 4 corners. We just wanted to make sure that everything else fits with the other systems before we added those, since that is relatively minor. Good observation.
Like same system as last year.
Same exact system with the eye bolts in the corners. Kyle.
What have been done on the new wheels to make sure that they are able to support the weight of the robot, to not going to crumble? What analyses have been done?
So we haven't done any FEA on the wheels themselves. We did make a prototype of it, and we basically just, for example, like a screwdriver and the chain on top. The ground pieces and trying to get like turn together. Try to just, we're basically just drop it up. Yeah, but seems pretty difficult.
So I think this is a little bit extra on that EDR, but can you elaborate on why that?
Yeah, so we did some analysis in CAD looking at this chain. It's kind of deceptive. You would think that with a chain that long, if you push down on it a little bit, you would change the amount of length of your total chain. Not really. The difference between fully untensioned and fully tensioned in this design right here, even with this big of a sprocket, is still only like one chain link. So that was the big concern, was with our smaller tensioner, we thought that we wouldn't be able to get enough tension to actually fully get 1 + 1 - 1 chain link if needed. But now we can.
So it's because you're mounted to the frame.
Yeah, because it's mounted to the frame and we couldn't lower any further, otherwise we would be mounting it to nothing.
It does look a little bit.
No, we know.
Like, if you could look at the, problem.
Yeah, we looked into a lot of different chain tensioner designs. This one we think will work. Kyle.
Because we did the drop down bracket last year, I believe. Is you're just avoiding it because you're avoiding the subject.
Okay, so last year it didn't work. Okay, last year it didn't work, and we ended up, last year the drop down bracket didn't have enough row to properly tension it. There could have been an even more complicated bracket that we did this year that had, like, we could have had like 2 sprockets on either side of the point that we pushed down to keep it like straight going into that point to try to take out more space that way. But at that point, I don't know that we're even like saving weight. It's definitely more complicated over just the big sprocket.
We've done a lot of looking into possible different designs here. Other questions? Yeah, Grant.
I think this might have been addressed in the last video, but with the using the box tube instead of what's the repairability like? Like if you need to get the chain out, it's strong.
We have a lot of access holes on the sides. And we are also planning on, the whole design was centered around ease of assembly. And so it will be very easy to remove the chain guard, which should allow repairability on the chain. The dust cover is also just 2 bolts to remove. Yeah, and we also have a ton of access holes everywhere. So we don't expect there to be too much difficulty with having to remove anything or repair anything if needed. Kyle.
Because it wasn't talked about in any of the other slides. What is the very large mass in this picture in the center of the frame?
Those are the motors.
Do they have a dust cover on them? Is that why they're so large? Okay.
The motors are very nice, except that they're not. All the motors have custom dust.
Yeah.
For the gearboxes, what are you using as the, what is the material?
The dust protectors?
Like the outside.
The frame itself, you're talking?
Yeah.
That's just going to be 1/8-inch box tube. Alex.
Is that going to be part of the frame?
That's going to be bolted onto the bottom of the frame with the ribbons.
How are those ribbons that are on the bottom?
Yes, this is the box tube, and then there are rivnets in here, and then in the frame, you can kind of see like one of them here. You have about little holes right here where it's just going to go on the bottom. Stick a bolt there, and then a painted Titan.
Yeah.
We have access holes on the top here. They should be on the front here. Maybe we have to add more access holes on the front. They are in the back here. That's what these big ovals are for. Yeah.
The 2 holes you highlight on the left rack. Those 2 holes.
These 2 right here?
No, the 2 above them.
Okay. That's probably correct.
Temperature is all set because it has.
The mountain pole center, you can probably.
Too late. No, it wouldn't have, maybe, but it just wouldn't have made sense.
Other questions? Questions from the chat?
Yes, so we're going to start off from the chat. How many were the old wheels for comparison?
I do not know off the top of my head. In kilograms, what is that?
1. That's, if you go, no, go back to the wheel. There's the weight in pounds. So these are like. Next question from the chat. With the tensioner, we based the passage in order to have the tensioner both be normal to the chain profile instead of being normal to the chain link. You attempt a design where the tensioner is pushed down instead of held by friction against the plates.
Can you repeat that?
So, with the tensioner, we base the passage in order to have the tensioner bolt being normal to the chain profile. So the way you have now, as opposed to being normal to the chain length, meaning the bolt would be going perfectly to how it is now. Did you attempt a design for the tensioner to push down instead of held by friction against the plates?
This was something that we did last year, and there were concerns about synchronizing the force downwards on the sides since the chain is not centered due to the gearbox arrangement. And we believe that the force on the sides will be enough with this design.
Okay. Another question from the chat. Also, I understand what's happening on your dust covers. Those might be annoying to align. You have a ton of potential sources of swap between the motor on one side and the motor on the other side, which could make your plastic dust covers not align.
Which dust covers are you talking about specifically?
Mike, which dust covers?
Those were designed by the chief engineer.
So, what's the question about the motors? Like,
Or do one now. Maybe I can this far away.
there are two separate dust. The dust cover is made of two parts, and there's two parts of the dust cover made one complete dust cover, third motor. But the two motors have two different dust covers. They don't. It's a weird angle. It doesn't look weird at this, but there's like space between the two.
I believe one of the dust covers also physically mounts to the motor and bolts itself, so it's fully defined in that way. Yeah.
So I think I did a little bit of explaining earlier. The tensioning for the chain tension.
It will be loosening this lock nut and then sliding it up or down and then tightening the lock nut through the slide. Potentially.
Yeah.
So at the beginning of this year, we did actually, we knew this was going to be a problem at the start because we knew it was a problem last year. At the speeds we're running, we don't need to, there's a very wide tolerance for what the tension of this looks like. Our biggest concern, which we believe this chain tensioner design does, is making sure that we can actually get plus or minus one link, because that was a huge problem last year in assembly. We had to adjust how our gearboxes were mounted because we couldn't get the chains to connect. Now we can and get a proper tension.
We have a full. We know it is not fun, but we know that we have. Well.
Any other questions? Alex.
Do you remember how much?
We had a test design where we had weight saving holes basically going along, fully along two of the sides of the box tube. That lost us about on an entire box, minimal space that we would have aged.
Yeah, we would expect maybe 0.5 kilograms of weight savings if we really went and optimized this thing. But then we need to make dust covers for all that. And so,
yeah,
it's just not worth it. Peter.
So how quickly can you begin manufacturing on the wheels?
Today's Saturday and then Tuesday. Yeah.
Yeah. So Tuesday, you can like go in Tuesday or Monday, you can make a reservation, go in and cut that plate.
That's my understanding, yeah. Any other questions? I think that might be it for Drivetrain then.
Okay, that concludes the first half of CDR. Who's the first half of CDR? So there's now going to be a lunch break, and we'll come back. Well, Alex, do you think we could squeeze in software? Absolutely. Okay, in that case, we're actually going to continue on to software right now. because we got through the mechanical team slightly faster than we thought, and so we've still got about half an hour before noon. So we'll have software come up here right now and give their presentation, and then we'll break for lunch and come back at a different time.
All right. Copper time. We're a little bit, this CDR is going to be a little bit different from everyone else's because we don't actually have any physical components that we manufacture, unlike every single other team, because we're software. Except with camera mounts, which we will get to. This DFMEA has not changed at all. A lot of it is just things can break, and we're trying very hard to make them not do that, mainly by just doing lots of testing.
Okay, so I'm going to start with the autonomy part. This is the same diagram as was presented at PDR, and nothing has changed. It's still the same game being played. The only note I added is that the software, a part of it, right, the scripts we use have been rebuilt and modularized differently, basically to adapt to the new competition for this year. That's the only update to that.
Yeah, so we're now going to use multiple cameras for our localization and for mapping the field. So we have successfully gotten 2 cameras and a LiDAR to add to that mapping and to detect obstacles. However, the update rate is quite slow, and LiDAR still has some issues, so we're going to continue working on that. And we may need to think about dust proofing for LiDAR, but it might just be fine with. So we're going to go test with we found an old LiDAR, so we're going to go test in the sand pit and determine if there's any issues with it. And if not, we don't need to really worry about dust proofing. Current positions are one's going to be off the back of the P&H box, one's going to be off the front of excavation, and LiDAR is going to be pointing down closer to the robot to get more accurate mapping of craters near the robot.
So we've also been working on some path following from last time. I believe last time we talked a little bit about one method that we had for path following. So there's 2 approaches that we're currently considering. One of them is pure pursuit, which kind of makes a smooth path follow procedure when you go from point A to point B. And the second one is more of a point-to-point path follower because a robot turns really well and translates really well. It just can't necessarily do those 2 at the same time very well. So we're kind of separating those to have kind of a better efficiency for our movement. Both of them are kind of cracking along pretty nicely. There's still a few tweaks that we need to make here and there, but overall it's going pretty well.
This year, as a new feature, we are adding status LEDs to the outside of the outside of the robot or somewhere near the P&H box. Where exactly will be decided later, but there will be space for them somewhere. And these serve no purpose to the people who are inside the mission control room because we have all of the data. These serve a purpose to everyone who is outside of the control room, which is going to be most of you. In general, so we have access to seven very easily distinguishable colors, and these are the LEDs are going to be at each of the 3 RGB LEDs are at full brightness, either one of them on, 2 of them on, or all 3 of them on, or all 3 of them off. These are what we are thinking of right now. These are going to be very easy to change, but in short, we have red for something is going wrong, green for the robot is in autonomy, blue for the robot is in manual control, and yellow and magenta are for something is going wrong. That's very specific. Like we've had a lot of issues with connection previously. So yellow would be like, hey, we are actually dealing with some serious connection issues and we're going to try and fix those. And white will be that if we're just sitting around and doing nothing, but the robot is powered up and ready, we can switch lights to white to say like, yeah, we know if we're ready, we're just waiting for things. We also have camera mounts. We have a total of 5 cameras and 1 LiDAR. There are arrows pointing to all of them. On the left image, we have the 2 front. We have 2 things that are mounted to the front of the robot by Excavation. We have one of our mapping cameras, and we have our LiDAR. And on the back, we have 4 cameras mounted to the P&H box. We have another one of our mapping cameras, 2 situational awareness cameras, and 1 camera that's pointing into deposition, so we can see how much red we have collected. The mapping cameras are fixed and mounted directly to the robot frame, so that they can't move, because that goes and breaks a lot of software algorithms if they start moving around. the LiDAR and all the three of the mapping cameras can pivot along one axis. So we don't have to decide what angle is best for them right now. We can just change them later. It's also useful for the LiDAR because the further out the further forward you have it pointing, the less good it is at detecting craters, but the more advanced warning you have of them. You can go and detect the craters, but we can only detect them 6 inches in front of us. That's not very useful because the robot it'll already be too late to do anything about that. And for our future plans, we need to do testing on the new system. A lot of our stuff is just, it works in sim, which is great and all, but it needs to work in the real world. Traversal and the path followers are the big one, because especially for pure pursuit, it is ready, it is there, and we have tested on the old robot. But there's a lot of configuration values that we need to go and tune and tweak to make sure that it works as expected, and those are very specific to the robot itself and to the specific wheels and the terrain it's driving on. So until we have the robot in regolith, we can't fix those values. We need to continue working on evaluating multiple cameras, making sure that we have enough bandwidth to go and transmit data, and making sure that the robot can run at an acceptable frame rate, that we don't miss stuff because it's just taking too long to update. We need to work with P&H to make sure the teensy pins are correct and that just everything gets wired up correctly. We'll be talking with you extensively. We need to go and integrate new motors into the main code after robot deconstruction. Our new motor code is ready to go. It is sitting in a branch with an open pull request, but we have not merged it in because we still need to do testing on the old robot, and that doesn't use the new motors. And we also need to finalize and create a global localization. So this year, there are more limits on where we can place April tags, and we need to go and just account for that change. And there's no question slide, but do you have any questions? Peter.
So first off, sorry, I had to go to the bathroom. When you say the tube camera plus LiDAR update rate is slow, how slow?
It ranges. The total, like each part of it can do like about 5 hertz, but then combining them takes a bit of time. So then the output is about like 1 to 2 hertz usually.
It's comparatively slower to build a map as to what we had last year.
Yeah, compared to last year where we had like 30 hertz.
We need to do more testing to go and see if that's fast enough. But at least driving this old robot around, it has been. The map updates fast enough because the robot can't really travel. Like Drivetrain's autonomous thing has been like around 1 foot per second, and that is more than fast enough to map. Even if we bump it all the way up to a meter or a yard per second, we'll probably still be fine. Although that's getting a little bit sketchy.
Okay. In that case, my next question about pure pursuit. So you say you have to tune, there are a bunch of values that we need to tune. Those are based on how the robot's actually behaving in this situation, right?
Yeah.
Are you at all concerned that, like MVC, we won't be able to get pure pursuit to actually work in the NASA environment? We don't have a perfect simulation.
So that's actually one of the reasons why we're considering two outcomes. So pure pursuit is our ideal scenario. You know, it's a smooth maneuver from point A to point B. It's the most efficient if our wheels can get good enough traction and translating and turning at the same time. But we are also prepared for the outcome that maybe that's not how it works in the regular. Maybe we turn really well and translate really well, but we can't do both of them at the same time. And that's kind of why we're also developing the point-to-point. So we do have a little bit of concern there, but that's also why we're kind of working on the back.
And also, pure pursuit is a much, much simpler algorithm than NPC is. NPC is short for model predictive controller. It has a model of how the robot will behave, and it predicts stuff and then chooses the best thing based on that prediction. Pure pursuit just kind of says, go toward the correct place. It's obviously a little bit more complicated than that, but it doesn't need to have an internal model of the robot. It just needs to have a correction factor. Like, you will slip a little bit more than you expect, so make sure you overcorrect a little bit here. Kyle.
Do you have anything in software that will detect if you are slipping excessively, or do you have ways to detect if the robot's getting stuck and not doing what you're
in terms of pure pursuit, Spark wrote that has a slip controller built in to hopefully adjust for that. In terms of like a more general sense, No, not right now.
We do have encoder. We do have encoder data. If it becomes an issue, we can compare encoder data. Say, hey, we're spinning the motors, but we're not going anywhere. We should fix that.
Yeah, our localization is based off cameras, so it's based where we actually are, not based off wheel rotations. And as Isaac mentioned, the Pure Pursuit controller has adaptive factor. It has a factor where it'll look at how fast the wheels should be moving, like are actually moving, and how fast we should be going based off that versus how fast we're really going, and base like increased power based off that.
Out of curiosity, you're talking about a lot about like our processing times today. What do you for?
The TNC is actually not doing most of our processing. We have a TNC 4.1 that is communicating with our motors and our load cells and our LEDs, and I don't believe it's doing anything else. Oh, those are actions. And we also have a Jetson, or a Nano. That is our main computer. That is what does all of the heavy duty camera processing and localization.
Do the
linear actuators do not have encoders in them. They do not have limit switches. They stop. We can watch when their current goes to 0. That is, yes, that is exactly what we did last year. We watched the current, and we said that when the current is lower than a certain threshold, we're down.
Actually, sometimes last year we just said go for 30 seconds.
We did also do that. Because the linear actuators are so wildly overpowered for anything we're doing, not much we can do can slow them down. So if we just tell them go down for 30 seconds, they will end up in the same exact spot every time.
That's what I thought.
Yeah, we don't have access to those.
But if they turn themselves off, then that's.
Yeah, no, they wouldn't break anything.
So with the current manufacturing plan, the idea is that the robot will be assembled a week before the NASA demonstration thereabouts. Is that enough time for you all to get the robot working such that we can demonstrate its functionality?
Under manual control, almost certainly. Under autonomous control, probably not. Assuming that we get a completely working robot a week before presentation, then it should be more than enough time. Obviously, yeah. If we get a completely working robot, we can probably put something together in like an hour. It won't be good, but a lot of one of the advantages we have is that we can reuse a lot of our work from last year, which means that we have basically everything ready and set. So in theory, we can just upload code to a new robot and press forward and it'll go forward. We don't know if that's going to be the case. Probably not. But in theory, we can. Hans.
On that note, if Drivetrain rushes the process and is able to get the functional drive base early, would that be beneficial to you if it doesn't have excavation or deposition?
That's a question for PNH. If you give us a drive base early and it has PNH on it, then yes, it would be extremely beneficial. The issue is that you just give us a drive base and there's no electronics on it, then that's not very useful to us. So that'll be a question for PNH when they come down here. Like, hi, what are you up to? Any other questions? All right, then in that case, we have 20 minutes until noon.
20 minutes until noon. Okay. We're going to do a quick poll. Okay, there are two options. Option 1, we do P&H right now and go to lunch, I assume slightly after noon, but then also by go to lunch, I mean we actually just finish CDR before lunch. Option 2 is that we go to lunch right now, come back at 1, and then we get P&H and wrap it up. So those are two options. Raise your hand for option 1. We finish CDR right now. That's definitely majority. So P&H, it's time.
Yes.
No.
How do I refresh the slideshow in here?
Hit escape and then go back.
Oh, okay, cool. Yes. All right. Well, hello everyone. It's PNH, and let's go here. So, system overview did not get formatted absolutely perfectly, but we have the power bulkhead right here. It goes into battery prop, power meter, overcurrent protection, PD board, connects to the e-stop. That cuts off all power once it's activated. Then that goes to the Jetson to the Teensy connects through all of our sensors. So like the sensor bulkhead, that will connect to mainly just like our load cells. And honestly, off the top of my head, don't remember what else is on there. But then we have our USB bulkheads, the USB-C that connects over to the USB bus, which then goes over back to the Jetson. That's where all of the cameras that are mounted on the box around here. Is it cursor? Yeah. All the cameras are going to be connected to the USB. We have our Ethernet port, so whenever we're doing testing, we can plug that in right there. We have an antenna mount that also goes to the Jetson. And then we have all of our motor bulkheads are located over here, which come out of our PD board to the breaker board. And our motors this year are the 200-watt motors. We went over that, and yeah. So, battery prop.
All right, let's talk about battery protection. So this is kind of a new board this year. And basically, as we were talking about in CDR, this is to ensure that we don't forget to turn off and disconnect the battery when we're up late working in the BIDC. So basically, we use the balance pins on the battery to detect and when it's too low. And then we have a latching relay that will just let shut and cut off the battery from the rest of the robot. We have our schematics, fairly small board, will work very nicely. This goes in between the battery and the power meter. So during the competition runs, we're just not going to have it in the PNH box at all. Again, this is just to ensure that we don't kill our battery. As such, we have our DFMEA that didn't get updated. Anyways, that there's not too much that we need to be worried about here, especially since we're not using it in the competition runs. It's not going to be crazy critical. All we want to do is to make sure that when the battery gets low enough, it's going to get cut off. Cool. PD board.
All right, so for the power distribution board, compared to PDR, basically the main change is getting rid of the 12-volt output. We figured out we weren't actually powering anything with it. So instead, we were using a 19-volt one that's powering the Jensen. For the topology of the converters, we're using buck converters for the step-down converters and boost converters for the step-up. Features-wise, all the outputs would have overcurrent protection. The 48 volts, which is connected to the motors, will have reverse input protection, which basically helps if the motors are spinning freely and current backfeeds somehow. And all the outputs, excluding the 19-volt output, will have individual output toggles that can be switched on and off, either physically or by the Teensy.
The reason why the 19 volt is excluded is because if you turn off the 19 volts, the gensen's powered off, and so it won't be able to start again. So 19 volt is always powered on. So this is the schematic. Compared to PDR, we got rid of one of the chipsets. This will lower theoretical efficiency a bit and will put more strain on certain components, but it should be able to deal with it still fine, and it will lower cost and also make the board smaller or make components space out more, which improves heat dissipation. So here's the board layout. It's a big board, 20 centimeters by 16 centimeters. Compared to the old design with one more chipset, it's actually not that much smaller, but things are spaced out more, and the layout is just much cleaner and should be better performing.
For the overcurrent protection, we didn't make too much changes compared to PDR. Originally, we decided to put like 3 or 4 of those at each output, but then we decided to just cut it to 1 and put it at the input. And the other changes is the resistors, the sample resistors. We have 4 resistors because since we change it from output to input, so it will handle more. It will need to handle more current and power. So we will have to put 4 of those in parallel in order to have higher power it can handle. And we haven't started working on the layout yet because we were still trying to get the footprint, but it should be done pretty soon, like this weekend. And we will try to make it as small as possible because it's just a small part before the input to the power distribution board. So ideally, it should be around 2 times 3 inches.
All right, for the DFMEA, it's basically the same as PDR. So basically, we're worried about the board shorting or drawing too much current and the protection's not working. Apart from that, nothing much changed.
As mentioned earlier, we have our teensy board, which will be powered through the Jetson, and we're going to use it to interface with our status LEDs as well as our motor data lines, linear actuators, and the load cells that are involved.
The main changes from PDR was we removed one of the max chips from the design. Thank you, software, for helping us with that. So we also included relay control signals for the PD board, as mentioned previously. We also have a test input power for external power testing, just in case we want to test just the teensy system. We added a bunch of test points for the various signals, and we also have the LEDs that Alex previously mentioned.
Here's the schematic and the layout. It'll be around 95 by 86 millimeters. As you can see, main changes from PDR, we got rid of the extra max chip, and added all the test points and test power.
The DFMEA is basically the same as PDR, just making sure we don't have installation errors, soldering errors, stuff like that. We don't want to burn one of the pads off or something, so just making sure everything's right on those terms. Yeah, that's pretty much it.
Right. These are the current sense boards. These are what are going to be measuring the linear actuator current to detect when they stall and have reached the desired full extension. So as we mentioned in PDR, we're going to have 2 different versions. There's no additional changes from them. So here are just the layouts right off the bat. And the DFMEA, it's just mostly focused on making sure the board actually functions. We can read the actuator current. It doesn't fail. And with one of the new parts, maybe the trace might overheat, but it shouldn't be a problem. So nothing else.
Okay, so I developed the CAD for the box thanks to Peter for all the help learning SolidWorks and all that. And reverse, yeah. So the box here it's 16 by 14 inches with a thickness of 1/16, like before. And we've made some changes. For example, with the motor bulkheads, we have 2 more of them now, and now they're placed on the underside of the box for just convenience sake with that. And also we have like, you can see over here we have the e-stop, we have the Ethernet which we moved to between these 2 depth cameras. We have the parts for the holes for the antenna right here. And like I said, the e-stop over here, and that's the deposition camera, and the D-sub sensor bulkhead is right there. And we have 3 USB-A bulkheads, 2 each, and 1 USB-C with 2, so 8 USB ports in total. And we have our latches here, and we have the gasket for making the lid close softer and also just more snug as well. And now that the CAD model is complete, we will send it to a company called Protocase that will manufacture it for us, because it's one of the things that we're not able to fabricate ourselves. So we'll receive that as seen, but just all the holes there. And yeah, also here we we use a bunch of bulkheads in order to dust proof all of our connections there compared to cable glands. We use bulkheads instead just to for ease of loosening and tightening that. And yeah, also a clear face so the inside could be seen. And Ryan can tell you a little bit more about the individual parts.
Yeah, so just to recap all of the connections we have battery bulkhead will be the Anderson power pole connectors. Like you mentioned, we've got 3 USB-A bulkheads, 1 USB-C bulkhead, 8 total ports, 6 motor bulkheads now, 4 for the motors and 2 for linear actuators. Got a D-sub connector for the sensor bulkhead and an Ethernet bulkhead as well for firmware and software flashing. The main insertion for the e-stop button and the antenna mount, as well as the cameras the software will be connecting. So our DFMEAs haven't really changed since PDR. The biggest change would probably be lowered the occurrence rating for the burnout on the bulkheads, just because now that we've picked out our parts, we've got a lot of clearance. The motor bulkheads are capable of handling up to 20 watts or 20 amps of power, where the motors won't draw more than 5. So even if there's a large spike in power on the motors, should not be a problem for the bulkheads. Outside of that, damage due to glue ports from dust, disconnection, not really large risks.
Okay, so I guess priorities moving forward, I guess any feedback that we might be getting, implementing that, finalizing our order bombs, just making sure we're getting as many parts as we may need, especially replacement parts for anything that's at risk of, burning out or getting any sort of damage. And then once parts come in, soldering, testing, putting everything together, we definitely do want to do a lot of testing with the motors if possible, just to actually see how the operation trends are, if you can probably help with that. But yeah.
Yeah, and I want to talk a little bit about how we're going to speed up the kind of manufacturing this year. Right now, we're planning on all of our surface mount components, at least the vast majority of them, we're actually going to have JLC solder them for us. It's cheap, it's fast, it means we don't have to do any of it. It's less tedious. And we'll also, to ensure fewer wiring errors, something that's been enforced is we now have, if you've seen on the layouts, there's connections listed all on the silk screen. So it should be a lot easier to tell where things are going and should hopefully speed up manufacturing a lot. All right. I think it's questions time now.
Yes.
Battery protection board. Yes. Yeah. Yes.
Yeah.
How quickly getting into
we have the knockout for the Well, okay, yeah, sorry. This power in knockout over here, we can change it to have as many like pins as we need. I think up to, what is it, 6, 8, something like that. 7.
Yeah, that's
Okay.
7.
Okay. 6, 7. Yeah. Okay. And with that, I guess we can add an extra bulkhead for that if we need to.
The currently, like, I think the theory that don't be running during active competition.
Correct. Fair. And
We can eliminate over during competition. That's fine.
yeah. Okay. I was gonna say, does anyone remember anything or what else is getting connected to the sensor bulkhead? I'm genuinely blanking on this, other than the load cells.
Yeah.
That's just 2 wires though, right? 4. Well, yeah. So 4, because we also have a 15 pin D sub, so we also have to count how many we have left over, I guess.
Yeah, we should have
Yeah, so
more than enough.
okay. Peter?
So you mentioned on the FMEA for the box, that the biggest concern is the bulkhead getting compromised because of dust. Right, so my first question is for, let's say, the motor bulkhead, how are they connected on the interior of the, on the interior to the rest of the, bulkheads?
Oh, pretty much you just have the connects sticking out from like the bottom of the box, and we're just gonna send those wires onto like the breaker board.
Yeah.
Yeah.
My question now is how is, if that breaks in competition, how well, how capable are we of replacing that bulkhead? Assuming
Well, the bulkheads, I'm not really too concerned of them potentially breaking, but more just if they do get compromised, let's say, you just have to clean them out. That's about it. Yeah.
I think we did, yeah.
Yeah.
It's not that bad.
On the current board, you have two birds. What is the other bird? What's the thing of them? Why are they both?
Oh, one of them is yours. It's basically so the standard version is just your Hall effect version. That's like bread and butter when we're doing current sensing. The new version, we're trying a new chip that does, it's called tunneling magnetoresistive sensing. It's just some fancy word for quantum mechanics. That's all I can say.
So is the goal to run the new current sensor and then get back something that doesn't work that will swing back to the traditional one?
Yes, we're just testing a new one,
Okay,
just
both of them.
Just to see if one's better.
The ideal is run whichever one gives better results.
Exactly.
I'm just not familiar with PCB layout. What are the sort of light red indication marks on the standard version?
You know. Yeah, the silk screen, as you can see, the silk screen here, we have all of our connections. And those are very useful.
No.
Seems kind of sus, Peter. Look, further over to the right. Oh, I guess.
Yeah, over the left.
Yeah. So the silk screen has no functional benefit. That is my official response to that question.
This is really the same question I'm asking that. When do you think you'll have your PhD back?
Completely done or functional?
Functional is that you give me the box and I have a fair drive system. I give software and I can test.
I'd say if we have no problems with shipping within 2 weeks to get it functional, we can get outputs out of it.
For that, we need the power board, the PC board, and the jet itself.
Yeah.
I think everything else optional can configure it.
Yes.
Yeah.
Backwards.
Yeah. But for complete functionality, that's be well.
It's,
So, do you plan on adding all of the mounting poles for the boards before you're not having prototypes make those poles, or are you planning on making those poles once we receive them?
I was planning on making those holes just in case, because once we actually get the boards, let's say, oh, this connector is actually much longer than we anticipated, and we don't want it bumping up against some other component. So the way we plan on going about it, very carefully, assembling the system, then marking out, like measuring all the distances from everything, and just trying to see where we need to make the holes, then either make some sort of marking on the box according to those measurements, or Alex also recommended making like a 2D, like just printing out a paper and then just marking that out and drilling through that. Something like that.
Yeah.
Yeah. Right.
I have a couple notes. First, I you are not going to have these in 2 weeks. Early Chinese New Year.
Ooh.
JLC, for the most part, for the options we need, they're still operating.
They are.
Yes, we can only get limited colors, unfortunately.
That is a shame.
All right. A couple other notes. Your e-stop, is that like directly in series with your power supply?
Yeah. That it gets a signal from the PD board and then just shuts off or the relay on the PD board. Because yeah.
And the to get to a lot of like spinning around really quickly.
Yeah. Where's it? Yeah, right there. It's like sticking out on the side, just away from like any moving parts.
Yeah, that's part of why we moved it to the other side, to make it like out of the way.
Yeah.
Cool. And then on slide 82, you had the power for the PCB. You're doing all your power traces as like fills on the middle layer there.
So they're fills, but they're not not the whole fill. The main fill that you see there is just for copper and balance, like balancing.
Yeah.
But for the power fills, they're small grouped together.
Okay. Yeah. Lots of very little traces. There.
Yeah.
We're not rated to your like 10.
Yeah, those aren't power traces.
Okay. Yeah. Everything. Right. On this board, so notice we have 3 chunky outputs, but I don't see chunky input.
Yeah, so the chunky input, it's a power plane. So that's the only power plane that kind of spreads the entire top half of the board. So this is pretty much the input, and it covers the top half of the board where the input is. And in terms of current-wise, power-wise, it really only flows through the top part. So these huge pads here. You see
Those are the individual.
Those are the switches, physical switches. Oh, I labeled that wrong. Yeah, that's supposed to be 24 volt. Yeah, that's a mistake. So for the 48 volts is these two, and the 5 volts is down here. And for the 24 volts and 19 volts is up here.
So you're
No.
Do you know lead time from prototypes to the bottom?
It should be 3 to 5 business days, supposedly. Yes.
Yes, so we have a latching relay here, which I guess wasn't screenshotted. Okay. A latching relay, it's a dual coil latching relay. So you get a signal, it will latch off, and then we can manually set it again to latch back on. And so that comes in, is like physically in between the battery and the rest of the robot.
So what does it look like? You said we're not going to have it during competition.
Correct.
What would you, would it really just be not plugging it in?
You can just not plug it in. Correct, yeah, so you wouldn't even connect the battery through here. You just bypass it with just some power pole connectors.
Okay, yeah, what is the actual thing? Power pole into the actual power,
Mhm.
and then, yeah, what happens after?
Oh, just go to the power meter.
Yeah, it goes, so, are you talking about during competition or?
No, it's just gonna be the same connectors for the power meter, just in line with that. So you could unplug it and then, yeah.
Right.
Yep. Alright, any other questions? Yep.
Have you verified all the stuff that's block?
Oh, this is sized.
Oh, cool. Nice.
Yeah. I may be missing something. This was. Yeah, fair enough. All right.
There you go. You've done the fair thing.
Yes. Yeah. For routing and all that. Yep. Yes.
If you go back to the actual model of the box, is the location, is it possible the location of the latches called the problem? They protrude down from the top of the lid a little bit, right? You need them to be moved, or are they?
Like the latches on the side here?
No,
Or-
the latch of the lid.
That should be fine. Yeah, how far does it protrude? Like more than?
A little bit more than an inch.
Yeah, that's fine.
Maybe about.
Yeah, that should be fine. Yeah, we get them on Mouser. Yeah.
We have a back, none of them work.
Alright.
Okay.
That's everything. Alright. Cool. Thanks.
All right, everyone. This has been a very good CDR. It's gone much faster than previous critical design reviews, which I think speaks to the good work that we've done throughout this entire season and the solid states of our designs in the moment. So here are some upcoming deadlines that we have to be thinking about as a club. The main one is March 10th is the presentations and demonstration to NASA. So ideally, we have the robot in such a state that it can move around and function at this point. So that's what's driving all of our manufacturing timelines that Diego will talk about in a brief minute. And then the next timeline is the month after that. The systems engineering paper is due, and then later that month is proof of life. By that point, obviously, the robot has to be fully functional, or at least fully functional to an extent that we can do for the proof of life video. So, minimum full robot movement, but ideally it's just done. And then May 7th is the student faculty registration from the competition, or?
For the competition, yeah.
Yeah.
So we need everybody for students, and then we'll also get faculty to register so that you're officially part of the team in NASA's eyes. Yeah.
Great.
All right. So this has been a great CDR. As soon as we walk out those doors, we're going to be officially in our fabrication season. Let's go. For the next 2 weeks, we're going to be working on the drawing files for all the parts that you guys have made over the past semester. We're hoping for 2 weeks. If we can get it within the first week, that'd be great. I want to prioritize all of the parts that are going to be important for the structural components first, and then get anything that's remainder towards the end of the second week. And then as soon as we finish up our drawing files, we're going to work on the actual component fabrication as well as the assembly process. I'll hopefully have an assembly plan for the various subsystems coming out this next week to discuss the route for what should be prioritized in our assembly process. And then this is all based on trying to meet the March 10th deadline for our presentations and demonstrations submission to provide software enough time to test. So we're hoping to have some wiring done on the robot in the final week before that presentation, and then provide a couple days, hopefully more than 2 days, but I've set aside 2 days for actual software testing for that deadline. And yeah.
So this brings us to now the engineering life cycle. So we've just finished CDR, which means that, as Diego just said, we are now officially in the fabrication stage. This will end with our test readiness review, which is set for a day or two before the demonstration, because this is when the robot is done. So it is assembled. So again, this is where we really hit the ground. We're going to be working really hard over these next couple of weeks because we need to get this robot done. But because of the great work you've done so far, that should be not too bad. And that brings us to the end of our 2024. Oh, yes.
On that timeline, there's one bit that is missing, and when is how getting deconstructed?
I wanted to clarify that. I forgot to clarify that with you. Is there a time where, I guess, what components need to be kept in place for software to continue testing while we're deconstructing? The main parts of the past year's robot that are going to be salvaged are going to be from Excavation. And I know that I think the last.
You can have it.
Okay, so we can fully dismount Excavation from Albi. And oh, okay.
I believe you had said that you wanted it, the drivetrain at least, constructed until at least Saturday.
Yeah, just a few more meetings just so we can have a little more time.
Okay. Yeah.
A lot of the tuning can be done on any robot in the real world. Pure Pursuit is at a point where it needs to be tuned on the proper robot. Point is not quite there.
Okay. Do you need the cameras for that, right? So we can't take off Excavation until, right? Because the camera's mounted on Excavation. So. Yeah. Okay. So in that case, we will be deconstructing last year's robot within probably this week or next week. And with that, any more questions? With that officially brings us to the end of our 2024-2025 critical design review. Congratulations, everyone. Give yourselves a round of applause. And now it's lunchtime. For everyone who tuned in, thank you very much for your comments. And
can everybody in person stay behind for a group photo, and then all of you guys can go get food? Please, just one quick photo.
Thank you all for tuning in, and hopefully we'll see you at the competition.
Thank you for your